Mystic teachings. While the Newtonian worldview is sometimes seen as denying the possibility of any such ideas, quantum mechanics, telling of a universal connectedness and involving observation in the nature of reality, denies that denial. What's up, YouTube? I'm Chris Beaudry, and today I'm going to be doing a brief summary and review of Quantum Enigma, Physics Encounters Consciousness, written by Bruce Rosenblum and Fred Kuttner. This is a physics book about quantum mechanics and the quantum enigma. And as I said, I'm just going to give a short summary on the book. I have no prior knowledge of quantum mechanics, so my summary should be a testament of how well Rosenblum and Kuttner are able to communicate the idea and the concepts. One thing I liked a lot about this book is that you don't need to do any math. It's all explaining the theoretical, or not just theoretical, but it's explaining through reasoning and describing the experiments about the physics of quantum mechanics, and you don't actually have to do any math. So it's good for physicists like me. So let's get started. So, when Newton was challenged to explain his force of gravity, Newton had a sufficient response. Hypotheses non fingo, meaning I make no hypothesis. He thus claimed that a theory need do no more than provide consistently correct predictions. And I mentioned this idea from Newton that a theory has to do no more than consistently correct predictions because quantum mechanics it's contrary to mankind's kind of innate perception of the external world, and it's contrary to classical Newtonian physics. And it's so contrary that when someone looks at it, they might be like, this can't be right. But it doesn't. They might say it doesn't make sense, but it doesn't really need to make sense. All that a theory needs to do is have consistent results, and the physics experiments that they describe in this book of quantum mechanics in the beginning of the 20th century all conclusively show that matter in atoms in the microscopic world exists as wavelengths of potentiality at one point. And they believe that when the wavelengths of potentiality collapses into an actualized matter in a certain location, they believe that's through observation. But as they'll talk about in this book, that's not necessarily true. All they really know is that at some points matter is a wavelength of potentiality with no distinct point in space, and at other points it's actualized in this space or that space. So let's talk about this a little more. So quantum theory tells that the observation of an object can instantaneously influence the behavior of another greatly distant object, even if no physical force connects the two. Quantum theory also tells us that an object can be in two places at the same time. Its existence at the particular place where it happens to be found becomes an actuality only upon its observation. Quantum theory thus denies the existence of a physically real world independent of its observation. And it goes on to say, classical physics explains the world quite well. It's just the details it can't handle. Quantum physics handles the details perfectly. It's just the world it can't explain. And what he's saying with this is that through experiments, all that we've so far been able to prove has a quantum enigma is the microscopic world of atoms and photons and electrons. There has yet to be an experiment proving the macroscopic world, meaning objects that we can perceive, such as a chair or a fan. But in theory, under reductionism, the microscopic world is a microcosm of the macrocosm, and that therefore quantum mechanics applies to all things. So let's get down to quantum mechanics a little bit and explain it a little further. So this is a hypothetical experiment. Consider a marble whose wave function is equally in both boxes. If you look in either box, you find out where the marble is. The probability then becomes unity in one box and zero in the other. The waviness collapses totally into a single box. That concentrated waviness, which your observation created, is what you call the actual marble. But our being able to see an interference pattern proves that there was no actual marble in a single box before you looked. And some precursor to this hypothetical experiment is that they have two boxes, and they have a machine that goes up to both, and the marble randomly decides which box to shoot the machine decides which box to shoot the marble into. And what they're saying is, until it observes, it objectively exists as a wavelength of potentiality. It's not like it's in one box and we just don't know which one it is. It is physically not in either boxes and both simultaneously. And although the marble experiment hasn't been done, there has been atom experiments where they shoot an atom into, it's the same thing, they shoot it randomly into one or two boxes, and they can tell from an interference pattern, which they describe in this, but it's too technical for me to get into in this short video, that they know that it's not in either box. It exists as a wavelength of potentiality until it's observed. So let's talk about the math before I show you the chart of that. So expressing the mathematics into words, the wave function of one of the states is the atom is wholly in the top box. The wave function of the other state is the atom is wholly in the bottom box. The wave function of the unobserved atom is the atom is wholly in the top box plus the atom is wholly in the bottom box. The atom is said to be in a supposition of these two states. It is simultaneously in both states. On looking in a box, this sum, or supposition, collapses randomly to one or the other terms of the supposition. Observation collapses the waviness, the probability, to a specific actuality. And I have a little crude diagram of the atom randomly shot into a box experiment. So in the top, you can see the pre-observation diagram. So you have two boxes, and the atom, which is that little swirly thing I just decided to represent as it, shoots into either of the boxes. But they can tell through inference patterns that it is not in either one of the boxes. It's a wavelength, which is a shading of potentiality, which is simultaneously in both boxes, either box 1 or box 2 at the same time. Whereas post-observation, or upon observation, and we'll find later that observation becomes an ambiguous term about whether it's a human or just a macroscopic object. But anyway, post-observation, it's either in A or B, and the determination of that is random. If it's in the A scenario, it's wholly in box number 1, and wholly not in box number 2. But if it's the B scenario, it's wholly not in box number 1, and wholly in box number 2. And what this determines that actualization and collapse of the wave functions is completely random. There's no explanation of that. All that we know is that we choose to either look in one or the other of the boxes, and then half the time it's going to be in one box, half the time it's going to be the other box. And we also know that before we looked, it wasn't in either, but simultaneously in both as a wavelength of potentiality.